I'm a physicist. This is going to be a physics talk, not a mathematician talk. I'm going to tell you. Should I talk louder, closer to my? Should I talk louder, closer to my? Coherent state have played a major role in loop quantum gravity. So I'm trying to give you which role and how they've been used and why it has been so important their use. They've been used in different manners. In fact, there are 3 different classes of coherent states. In addition, each one coming in variants, but I will not go into the variants. 3 different classes of coherent state have been used, and I will tell you what are they and what kind of physical problem they were introduced for solving. The naming varies depending on whose literature you refer to. I will start by giving you a little bit of the history of how this came about, because I think this clarifies a lot how a lot of people here in this room, without knowing it, have affected the research in loop quantum gravity. So I'll say a few words about history, just to be very, very short. Then I will sort of switch mode completely and just give you the theory, the basic of the theory. There is a Hilbert space with some operators and dynamics. I will tell you what it is that we use for describing quantum gravity, so the theory. And then in trying to make sense of the theory, and in fact also in building the theory itself, coherent state played a major role, as I said, and at 3 stages, or for solving 3 different problems. So there are 3 classes of coherent state, 1, 2, and 3, which I would call intrinsic, extrinsic, and non-local. And they were introduced for addressing specific problems of understanding what kind of physics quantum states represent, or what kind of geometry quantum state represent, because this is quantum gravity. So it's a quantum aspect of geometry. So it's quantum state of geometry. I'll get into that. I'll say what these things are. Let me start from history. And I think I don't need much space for history. I can stay here. So I want to tell you the various stages in which came about from the perspective of myself, how I have seen this, this story. So for me, all this came when I was a student and I decided to go into quantum gravity. So we are talking, you know, ages and ages ago. Somewhere in the early 80s. I went to London because at the time the guru of quantum gravity was Chris Isham at Imperial, and I studied Isham's beautiful quantization lectures, and he was collecting ideas and so mapping the territory for quantum gravity, and I tried to learn from him, spending some time with him, and perhaps the main lecture I got from him, which turned out to be useful, may sound familiar because it's the same words this conference was opened from. So this from Chris Isham, and was do not stick to canonical commutation relation, and the name associated to it was a certain Clowder. And now I'm sort of 60, I'm here, and there's this conference, and the conference open with John, who gives us a speech saying, well, I have a message to you, don't stick to canonical commutational relations. The reason Eichhorn thought was important is because standard quantization, standard quantum field theory did not seem to work for GR, so something else was needed. And going away from canonical quantization relation, according to Chris Eichhorn, was the right thing to do. There were many indications of that. One of the key one at the time, which John himself started from, is that the determinant of the metric tensor of G mu nu has better to be larger than 0, which means that the field spaces are not, is not a linear space. You cannot go to negative determinant, you cannot go to minus G mu nu. At least in some, this is a three-dimensional one, but I don't want to go. And so, how can one implement that in the quantum theory? Canonical commutation relations, PQ equal I, of course, force the spectrum of this to be the real line immediately, right? Just exponentiate one and you get an operator that shifts this from minus infinity to plus infinity, so one line demonstration. So if you want something which stays positive, you need not to have canonical commutation relation, very simply. And on this very much Johnny idea, Chris was trying to build upon that. In fact, I started from that. Shortly after that, I went to the United States and I met two guys. One is Lee Smalling, and one is Abai Ashtekar, who were completely focused on quantum gravity, sorry, and there was no loop quantum gravity at the time. There were very few people doing quantum gravity at the time. In fact, the list was not much longer than that. And what Ashtekar had been doing, was a reformulation of classical general relativity, which seemed convenient. And we'll see why it seemed convenient, in which instead of the field G mu nu, the pseudo-Riemannian metric of space-time, he used two fields, one of which is a SU2 connection, and one is essentially a triad. A triad is the square root of the metric, and is three vectors, essentially. So three vectors, A is 1, 2, 3. This is an SU2 connection, like the field of an SU2 Yang-Mills theory. These are canonically conjugate to one another. The dynamics of general relativity from the Hamiltonian point of view is far easier with these variables than with the original Einstein variables. So this seemed to be completely unconnected to what I was learning in London. But Lee Smalling, with Ted Jacobson, using these variables, was able to find some strange solutions of the Wheeler-DeWitt equation, which seemed to be the equation of quantum gravity, solutions related to line exponentials of the line integral of the connection along loops. So this is a loop, a line in space. This is an SU2 connection, so this thing here is just an element of SU2. And you sort of parallel transport with a connection from here to here, you get an element of SU2. Now, one of the ideas of John was that instead of taking Q and P, you should study things like the product of PQ or the exponential of these. So instead of studying the algebra of these things, you can study the algebra functions of these things as taking as main algebra to quantize. And here there was an object that seemed to play a role in the theory because it was solving quantum equation, which seemed to play a central role in quantum gravity for some region. So the idea came out to take these ideas and apply them to these variables here, and instead of quantizing canonical commutation relation of A and E, quantize sort of H and something like that. And that is loop quantum gravity. That was the origin of loop quantum gravity. So it's a non-canonical commutation relation quantization of generativity in the Ashika variable, where instead of using the connection, you study the exponential of the connection. And for reasons which became clear much later, a lot of things simplified, and things seem to get together in a rather surprising way. Roughly, the classes of operators that in loop quantum gravity we want to consider as fundamental operators are these group variables which are associated to a loop, to a line. So for every line, you have an SU2 element. And something out of that, this is actually, from the mathematical point of view, a two-form. So two-form you can integrate on a surface. So given a little surface, sigma, you can integrate E on the sigma, and you get something which is just labeled by this sigma here, that since this is a vector, has a vector index, it's in R3, it's an internal R3. Internal R3 is essentially the algebra of SU2, so it's naturally an SU2 object. And the reason I'm mentioning that is because this operator here and this operator here have canonical commutation relations, which are not, sorry, have commutation relations which are not canonical, but are very pretty, and are the following. If you have one of these SU2 element associated to a line, and this E associated to a sigma, the commutator of the two, or classically the Poisson bracket of the two, is 0 if the line does not go through the surface, and if it does go through the surface, so imagine you have a line here going to the surface, this is gamma, then there is an intersection point. The line is breaking in two lines, let me call gamma 1, gamma 2, and what you find here is I, gamma 1, gamma 2, with a sigma matrix stacked between the two, with an index in the algebra, which is this index algebra, which is this vector index here. So this algebra here... There's a C number on the right? Sorry, it depends what you want, which version. If you want the Poisson bracket of the two, then there's no I here, and you have a G, the Newton constant, which comes into the action of the theory. If you want the commutator, there is an I here, and you have H bar G, which is the Planck length square, and is the corresponding commutator in which you stick an H bar if you do a quantization. Yes?
Yes. So you impose that...
you start from that algebra.
Will become the commutator.
Yeah. So it is...
In some sense it's canonical, it's still canonical, but...
In some sense, yeah. I'm just giving you history here. I'm not giving you a construction of the theory. This was a starting point, and from there, loop quantum gravity came about. It is, in a sense, still canonical in the sense it's still the Dirac idea that the Poisson bracket tell you something about the quantum algebra. It's not canonical in the sense there's no PQ, there's no creation annihilation operator, there's no standard Fox structure, there's no plenty of things. So the result of all that, I would say, because of John originally, was a blessing and a curse. A curse is because we started not working with PQ variables, with A and A dagger, creation annihilation operators, which meant that nobody in particle theory was understanding what we were doing. And for decades, every single thing we were doing, particle physicists would say, what the hell are you doing? There's no creation annihilation operators. Where are the particles? Okay. The blessing was that this works for doing a quantum theory, not on a geometry, but a quantum theory of geometry itself. So it turned out to be the key that opened the possibility of doing a quantum theory of geometry itself. So let me stop with sort of.
Please use your middle board.
Yes, now I go to the middle board because I'm going to go to the second point, which is the theory. I'm not the only one who is talking about this theory here. There was a talk by Benjamin Blair the day before yesterday, and there will be a talk by Simone Speziale tomorrow. Both of them actually have filled and will fill up some details which I left around. So there's a lot of complementarity between the two. But the object we're talking about is the same. The theory we're talking about is the same, and it's this one. In particular, Simone tomorrow will illustrate this coherent state in a much more, I believe, detailed way of what I'm going to do now. But I want to give you the idea of the theory that came out from that, as it is today. So forget physics for a moment, forget the coherent state for a moment, and then in this theory I will write the coherent state and say what they do. And I write the mathematics of the theory, all the basic mathematics of the theory, and then I discuss what it means, what it is. So it's a theory, it's a quantum theory, so it's made by three parts. There is a Hilbert space, there is some observable algebra, and there is something defining the dynamics. If you want, for a particle, L2 of R, P and Q operators, and the Hamiltonian. For QED, Fock space, Gray annihilation operator, and Feynman rules. Or for lattice QCD, the L2 of group variables on a lattice, etc., etc. So you can. So what is a Hilbert space? So I'll give you the three elements. So first the Hilbert space, and the Hilbert space is a space with some structure. It's defined as a limit. One can do the same thing with Fock space. One can define the n particle state and then take the limit. So there's something similar. So it's defined as a limit for some gamma going to infinity. I'll tell you in a moment what is gamma of some Hilbert spaces labeled by gamma. So what is gamma? Gamma is an abstract graph. Abstract graph means a couple which is a finite set with n variables, which are called nodes. It's a finite set. For a physicist, this is a certain number of points, n1, n2, so n nodes, and there are n of them, big N of them. And links. Links are oriented couples of nodes. So it's a subset of the set of the square of the set. So you can think of this as arrows, lines connecting nodes with arrows. Some of them, not all. And there are L of them, big L, and we call them little l. So this is a graph. So for each one of these graphs, there's a Hilbert space. And then there's some mathematics that tells you how graphs sit into one another, and the Hilbert space corresponding sit into one another. And there's a notion of projective limit that's not particularly important for here. So this is, for given gamma is a subspace of the full Hilbert space, which is sort of a truncation of the full Hilbert space. And I'm going to define what is this Hilbert space. So to define it is two steps. I first define a little bit larger space, and then I project it down the relevant part. So the larger space is an L2 space of SU2. L2 is the Haar measure on SU2, is a standard one, which to the power L, big L, the number of links. So the way you think about this is that this is a space of functions of big L SU2 variables, each one associated to one of these links. So to each link there is an SU2 variable, this is oriented, and you have a function of that. This is not very exotic, it's the same Hilbert space of lattice QCD, of SU2 lattice QCD. So obviously it has to do with the transport of the Aztec connection, but this will come later, it doesn't matter for a moment. Now, this knows nothing about the graph, right? The only thing it knows about graph is how many links are there. So now the graph is coming in. How it's coming in? Well, I'm going to divide this space by something which I'm going to call gauge, which is the transformation in which I take one of these SU2 elements and I transform as a gauge in the same sense of lattice QCD. So given a lambda in SU2 per each node, I say that this is gauge equivalence to lambda n HL lambda n prime minus 1, where if this is L, this is n, and this is n prime. So this is the source and the target of the link. So all the states which are invariant under this transformation form a subspace, is a proper subspace, SU2 is compact. So I can quotient by that, and I have H gamma, which I wanted, which sort of in the trade we write in this way, SU2 to the L divided by SU2 to the N, because this is the size of the gauge group. Of course, if you say that, you have to say how this divide that, and depend on gamma, so I'll put a little gamma here to say in which sense SU2. That's a Hilbert space. Basically, everybody who does loop quantum gravity, one way or the other, works with this Hilbert space.
Sorry, again, L is a node of.
There's some logic in the choice of names. Yes, so, okay, so this is H. Of course, Hilbert space are all the same, right? What the mark is the structure and size of the operators that we have there. So what are the operators? What is the algebra of the operators? So here, there are two classes of operators. Basically, they are going to be related to these and those, which are the group elements themselves. I write as a physicist. The group element act on the state diagonally by multiplying the state by the group element, which is a bad physical notation. So AB. So any function on the group becomes an operator which is simply multiplying this. So there's an L here. An L, each one of these. So for instance, let's take a basis of functions on SU2. A basis of functions is given by the Wigner matrices. This is in fact an orthogonal, under the SU2 structure, is an orthogonal basis in SU2. So each one of these, for every J, M, and N, is a function on the group. So there is a D, J, M, N operator for each L acting on P of HL, which act diagonal. Just multiply it for DJ, M, N of HL, psi of HL. I'm just saying stupid things. I mean, you have a Hilbert space of functions on such space. Any function on such space act.
H is chosen for the Hamiltonian?
No. H is here. All these little h's are elements of SU2.
The big H.
Is a Hilbert space. Is a Hilbert space. Is a collection of all the states, the space of all the states, the quantum states. If you want, the Hamiltonian is going to be hidden here in the dynamic. That's the dynamical part. I first define the kinematics, which is highly non-trivial because it's not the kinematic of particles, or it's the kinematic of space-time itself, of the geometry of space-time. Now, more interesting is the brother. All these commute with themselves, right? This is all diagonal. It's the brother, which is the E operator. So what is the E operator? I should find it here because it's still in the algebra. What is the E operator? Well, it should be a derivative, some sort of derivative. So on a group manifold, you have a derivative, which is the left invariant derivative. L psi of h, right, is the limit epsilon going to 0, 1 over epsilon, psi of h e to the I epsilon sigma I minus psi of h, the standard invariant derivative. So we put a little I here and a little I here. This is a Pauli matrix. This is a generator in the SU2 algebra. And I have one of these for each L, right? Because for each, so I have a, yes, there's a subscript L somewhere. Here is, so let me not write it. I have LIL, which is the one that acts on the Lth element inside here, right? And the E operator is just that, with an H bar G for dimensional reasons, because it will have a physical interpretation. It's for some reason for which the momentum operator has an H bar in the definition. Here H bar goes always together with G. These are the basic operators, and notice that they don't commute with different I with one another. So as SU2 algebra, obviously. And of course they don't commute with H, obviously. I mean, where is this L sitting in the graph? Well, the H is sitting here, the L is sitting, if you want, the left invariant vector field act here and the other act here, in terms of how they transform. One act on the left, on the right, and one on the left of the operator. Finally, there is the dynamics. The dynamics is here, okay, so I have to tell you what the dynamics is. I don't want to go much into the definition of the dynamics. The way the dynamics is defined is simply by giving a map called W on the Hilbert space itself to the complex numbers. I think it's better I don't write it explicitly. It will take me a few definitions. I'll just mention that there's SL2C. You'll see why in a moment in it. I just want to tell you that there is a linear operator from the Hilbert space to the complex number, and when I will tell you the interpretation of that, you will see what it is and how to think about it. Stop, because I want to talk about interpretation. What are these things? What do this Hilbert space with these operators mean? And you will see that to actually really make sense of them, we need coherent states. Otherwise, we're completely confused. So what are they? Interpretation. This is just a bunch of mathematical definitions, right? No more than that. How is it related to physics? So where is it? What is physics here? Okay, so this is supposed to describe GR, generativity. And generativity is about Riemannian manifolds, or pseudo-Riemannian manifold. Pseudo-Riemannian space-time. A space-time which is a pseudo-Riemannian manifold. Four-dimensional, of course. The world is four-dimensional, even if some colleagues of mine say it's 10-dimensional or whatever. Now, inside, take a four-dimensional space, our space-time, and take a region, R, a blob, finite, compact. This will have a surface, which I call sigma. Most of the time when we think about these regions, we think of these sigmas to be always space-like, so we think of the region like that because it's simpler. So it's a space-like part, and a blob.
When you say pseudo-Riemannian, you mean 1-3 signature?
Yes.
Not 2-2.
No, 1-3, yeah, the standard GR one, yes. So sigma is a 3D manifold that inherits from the pseudo-Riemannian manifold a geometry, just a definition of distance that goes down to it, and an extrinsic geometry, how it's folded in 4D. So it has an intrinsic geometry, and it has an extrinsic geometry. Okay? The great idea of Gauss to distinguish intrinsic and extrinsic, Riemann, in fact, intrinsic and extrinsic geometry. So extrinsic geometry is how this normal is a different direction, this normal here, which of course I don't see on the manifold itself, but on the manifold itself I see its own curvature, and it has an intrinsic geometry. So let's take this, this sigma, let me draw it here. This is my three-dimensional sigma. And I want to describe its geometry. Let's start from the intrinsic geometry first. But I want to describe it not exactly, but in a truncated way. This will correspond in a moment to this truncation here, choosing one graph. Choosing one graph is like not studying the full geometry, but a truncated geometry. How do I truncate it? Let me triangulate it with some tetrahedra, say. And if you want to think physicist, think that these tetrahedra are small, so that with flat tetrahedra you can approximate a curved Riemannian spacetime.
Inside sigma?
Inside sigma. Inside a three-dimensional sigma. Of course, in doing so, you lose information about the geometry, and that's a truncation. You're forgetting some degrees of freedom, some high-frequency degrees of freedom. If you have a triangulated sigma, you immediately have a graph. How? Well, you just put a dot inside a node inside each tetrahedron, and you have a link connecting any two tetrahedra which are next to each other, separated by a surface. And you can immediately have two quantities so given a triangulation, you have a graph. And in fact, if the triangulation is in real triangulation, the graph is four-valent. If it is an arbitrary cellular decomposition, the graph is not four-valent. Let's say triangulation four-valent graphs here. Each tetrahedron corresponds to a node. Each triangle corresponds to a link. And if you choose a point and draw this line explicitly, since you had a geometry to start with, I started from a four-Riemannian geometry, you can go to Ashoka variable, compute this connection and this triad. Take the parallel transport of the Ashoka variable along these lines, of the Ashoka connection along this line. So compute an SU2 element, which is this thing here, along this gamma, and on each triangle, compute E associated to this triangle, but the triangle in one corresponds to the L, integrate on the triangle well, this is a two form, this is just labeled, no, this is labeled by L, this is the triangle dual to L. So you see, this truncation gives you a set of classical quantities which are precisely one-to-one correspondent with the operators that I have there. So now the interpretation of these operators, so this is a quantum theory that quantizes these variables in the truncation in which I neglect the higher the shorter distance degree of freedom. And the more I refine my Hilbert space, the more I get everything I want.
But I don't understand why the structure group is not SO3 rather than SO2.
Because nobody does. Because for the same reason for which the electron, and nobody knows why, is described by a representation of SU2, not SO3. I mean, the particles of particle physics. One way of viewing this is that the classical theory actually knows the algebra, not the group. In the classical theory, there is no knowledge of the group structure whatsoever. There is only knowledge about the algebra structure.
So somehow you assume that your manifold sigma should be spin.
Yes, absolutely.
Okay.
Absolutely.
Then I understand.
Absolutely. Otherwise, it doesn't work.
So in the Hilbert space, in that case, you remove all half integer instead of taking all half integers.
Otherwise, you would. Yes, you don't. You keep all the half integers. Yes, exactly.
I think it's very important.
Exactly. Oh yeah, no, absolutely. Absolutely. Yes. Yes. No, absolutely. Good. So let's see immediately. Suppose this is the correct quantum theory that describes the quantum geometry of this classical geometry, which is the one that we know describes the gravitational field. Immediately, oh boy.
7 minutes.
How much?
7.
Oh, okay. So immediately, okay, so I'm I'm getting to the coherent state now. Immediately, you have some consequences which are rather dramatic. And here is one consequence. This is a triad. Let me ask, what is this? Was a pseudo-Riemannian object. This is a space-like. So this is there's a metric here, and I can ask what is the area of this triangle. And the area of this triangle is easy to a few lines to see, which is ELI, ELI. And this, in the quantum theory, is the scalar product of two of these in this index here, in the algebra, in the SU2 algebra. And this is h bar g squared, the Casimir. But the Casimir has discrete spectrum. So according to the standard interpretation of quantum mechanics, this is telling me that the area of this thing, which is a classical dynamical quantity, has discrete spectrum in the same sense in which the energy of a harmonic oscillator has discrete spectrum. So this theory tells me that the area of triangles is quantized. And of course, I know the eigenvalues are things like that, jj plus 1, where j is half integer. So the area eigenvalues are labeled by a quantum number, which is a spin, and is discrete. So you say, great, I haven't have a physical interpretation of these states, but there is a problem. And this is where the coherent state came in first. And the problem, oh, I was supposed not to use my hands to. Let me pick a basis in this Hilbert space by giving the quantum numbers. What I can do is to choose eigenstates of the area. So on each link, I will have a quantum number which is a spin associated to that particular link. These are not sufficient. They don't give a basis. It's still degenerate. I need to add something else. Well, it turned out that it's not very hard to find another quantity to get a complete basis, which is the volume of the tetrahedron. The volume of the tetrahedron, in fact, the volume square, is a triple product of three arbitrary, it turned out that doesn't depend, 1, 2, 3. So this is a node. This is 1, 2, 3, 4, the 4 links. There are e's associated to each one of them. Because of gauge invariant, it doesn't depend which one. I always get the same quantity. I can diagonalize this. This is also a operator there. It has discrete eigenvalues, and I can take its quantum number. And this is called the spin network basis. And is a basis in the sense that there's 4 quantum numbers. So these quantum numbers, the operators A for each L and V for each node, are a complete set in the sense of Dirac. Namely, they commute with one another, and the quantum numbers distinguish all the states. Fantastic. We have a basis in which the geometry is fixed. For each tetrahedron, we know its volume, and we know the 4 areas of the faces, so we know its geometry. Bring it together, we have the 4 geometry. We have the geometry of everything. No, why not? Because the geometry of the tetrahedron forms a 6-dimensional space, not a 5-dimensional space, right? You fix the geometry of the tetrahedron, for instance, given 6 length. You can always fix 5, and the 6th one you can still open and close it. So this geometry here is something which classic is determined by 6 variables, and these are only 5. What's going on? Well, nothing strange. It's going on the same thing that when you quantize the angular momentum, these are 3, Lx, Ly, Lz, but then in the quantum theory, you can only diagonalize L squared and Lz, only 2. The rest is spread. So you cannot have sharp all 3 components of the angular momentum. You can have sharp, say, L squared, Lz, but then the other 2 are completely spread. So this state in which area fixed and volume are fixed is not at all a state with given areas and volume and some shape of the tetrahedron. It's completely spread on all possible shape of the tetrahedron, which have that area, that volume. And there's a one parameter family of this. It's totally spread.
It's called degenerate.
It's called degenerate. Yes. So how do we fix this? There's no way to fix it unless we use a coherent state. We want a state such that, given a classical geometry, so given 6 number, gives me a sort of linear combination of these objects, such that all the geometrical quantities of the tetrahedron are not sharp, but have small variation.
In this construction, they depend with same instant. If you have two triangulations which have same incidence graph, right? Does it depend the way you triangulate? Does it depend the way you triangulate your boundary sigma? If you have 2 different triangulations with the same incidence graph gamma, do these considerations depend?
They better not once I go at the level of the dynamics.
Okay.
So when I fix a graph, then I'm staying on that graph.
Yeah, but you could change the triangulation.
I could change the
Taking all their platonic solids?
Yeah, no, these are graphs. So
Yeah, no. The question is perfectly well posed. A graph is an abstract graph. I started from a triangulation sitting in a given. So you correctly say, what about if I change the triangulation? So at the level of dynamics, you should be cancelled. This depends. It should be cancelled. It better does. Absolutely. So how does those coherent states work? First, this was the solution to this problem came in a beautiful work, spectacularly beautiful work, my idea. We struggled for that for very long. And the people who finally solved that cleanly, Simone Speziale and Terra Levin, which is the first apparent of coherent state, the first of several. These are the intrinsic coherent states. And what they did was, it's very nice. They went back to the Hilbert space with a tilde before factoring out gauge invariance. And they realized that I can describe the tetrahedron directly with 4 vectors, n1, n4, which are 4 vector normals to the areas. And they realize that this Hilbert space, let me do it here. I'll try to do it fast in a simple manner. Let's see if I don't lose you on that. So H tilde gamma is L2 of SU2 to the L. Okay? So this is obviously the tensor product over L over L2 of SU2. 50. Now, L2 of SU2, this is Peter Weil theorem, the fact that the D variables form a basis. I can write it as the sum over spin so I have this form a basis, djmn. So I have a sum over spin. And then these are a basis in the representation, so this lives in the Hj tensor Hj. Okay? Now you can switch the sum and this and the tensor product, and this is the sum over 1j label per each L of the product over L of the links of Hj tensor Hj. And where do they sit in the graph? This is this index here, which of course transform with a gauge transformation here. This is the index here, we transform with a gauge transformation here. So let me think of this H here and this one here for all the graph, and rearrange all this by node. So this is a sum over JL of the product of the nodes of Hj1, let's say that they're all 4-valent, Hj4. So each node has its own little Hilbert space, and the tetrahedron sits in this Hilbert space here. In fact, it sits in the gauge invariant part, in the invariant part of this under the diagonal action of SU2. But that's allowing me to take in each one of these a state such that the operator E has this eigenvalue, and then take the invariant part of it by projecting it down. And how do I do? Well, it's very simple. Because on 1H gamma, you know how to do it. It's a parallel. You take the state Jj, and this clearly is an eigenvector of Lz, and it minimizes Lx and Ly. So if I take this and I rotate arbitrarily, I get, this is a blob on the sphere here. If I rotate, I get a blob on the sphere here. So I can take this, I can rotate it with a group element n that rotate a z vector into n. Z vector is in the z direction. And I get something which I call Jn, which is a state which is the n direction. I take 4 of these, and then I project it down to the gauge invariant part. And I get something which is usually notated as 4 spins and 4 vectors. and is a projection, so the integral of SU2, dh, h in SU2, h acting, it acts by rotation on J1 N1 tensor J4 N4. And this thing here, so you give me a tetrahedron, you give me 4 areas, you give me 4 vectors in R3. I use this formula, and I produce a state which is a coherent tetrahedron. It's a state which is not picked on the geometry of the tetrahedron, but is its expectation value of the geometrical operator are those of that geometry here, and the spread is small.
So is it correct to say that this gamma encodes the type of Feynman diagrams that will appear in your theory?
No, because this is only at the level of
the gamma, not just the nodes, the way they are.
no, because this is only at the level of states. Then I have to say how this evolve from here to here, and that's W. I have used all my time, so I have to stop. I'll just mention what are the other ones very fast, because once you get the idea, the rest is immediate. What are the other ones? Well, those states here, which were introduced by these people here, make the intrinsic geometry as coherent as possible, as sharp as possible, as coherent as possible. But the extrinsic geometry, how these surfaces fold into phase space, this is not in the E variables, is in the group variables. So now I have to write states in which both the group variables and the intrinsic geometry variables are as sharp as possible. And that's are the extrinsic states, which in the trade are called Thiemann state, which are essentially how SU2 coherent states, to which one does this game here of taking 4 and projecting down. So this describes the full intrinsic extrinsic geometry of the 3-dimensional surface. Describe a state who has the given intrinsic extrinsic geometry in the same sense in which a coherent state with P0, Q0 is picked on P0 and Q0. And this is link by link. And then the question was, can we do that on the graph, including the correlations between different links? So can we have states which are picked on a given geometry, but the fluctuates not only link by link, but there are fluctuations which are correlation, like in the vacuum of quantum field theory. So what the coherent state served in the theory was to connect the formal quantization, which was clear in terms of eigenvalues, eigenvectors, but was hard to connect to a semiclassical geometry. And now we have an increasingly clean understanding of how to write semiclassical geometries in this context. I was hoping, but I've used all my time, to tell you an application. I'm not going to tell you application, but I'm going to tell you the title of an application. We are right now computing the time it takes a black hole to explode. Classically, a black hole forms and stays there forever. But quantum mechanically, nothing is forever in life. Quantum mechanically, there is a finite probability for a black hole to explode. So how do we do it? Well, we have a geometry in which a black hole forms and then explodes, which solves the Einstein equations, except where there is quantum tunneling. So on this geometry, we take a surface around the black hole. We know the geometry, intrinsic, extrinsic. We write the coherent state corresponding to that geometry. We compute the W of that coherent state, the probability amplitude for this to happen. And this gives us the probability amplitude for a black hole to explode for any given mass. So we compute the lifetime of a black hole as a function of the mass. We are very much immersed in this calculation. So this is an application of quantum gravity with potentially in principle measurable astrophysical quantity, can only be done because we have these coherent states that connect the classical geometry with the quantum states. Thank you.
We have not much time, but maybe one question.
Sorry for...
What is the lifetime as a function of the mass? What's the answer?
That's a question we are debating every day here. We have a formula. We have computed a formula within inner truncation, which is very complicated. We're trying to extract from this formula. I expect is this one. That's what I expect. Hawking evaporation is m cube. This is in Planck units, right? So this is immense time. It's for a stellar black hole, it's 10 to the 50 times the life of the universe. This is what we believe is reasonable. Well, I believe is reasonable, at least. We're trying to see whether it is this or not. And this means that a small black hole with a few centimeters, the mass of a small planet, could be exploding today if it was primordial. Primordial. So primordial black hole could be exploding today. That's why we're interested in these things.
So there was some other question. I don't know if you... It's a long question. Or...
So these coherent states are standard one parallel of coherent states related to groups?
Yes, these are the parallel of coherent states, exactly the standard one. Exactly and once we go to the other coherent state, or essentially the whole one, the HAL one, we take 4 of them, and then we project it down, which is like considering up to rotations, essentially, up to SO3.
And you can
they're absolutely standard,
classical evolutions. You recover Palatini, maybe Einstein's equation in the Palatini form, because you have used triads and all.
Yes, and in fact, this also was done with coherent state. If you take this W, you take this W, the amplitude for a state on a surface around the region, and what you want to get is the Hennenfent function, the action, the exponential of the action for that boundary geometry. For that, you need a coherent state on the boundary geometry. So this was obtained by Barrett and his group in Nottingham. And he proved as a theorem that in the first order, in whatever is relevant, you get an action which is the Palatini version of the discretized, the Regge Palatini version of this thing.
Okay, so let's thank the speaker.
Thank you.